Bismillahirrahmanirrahim. In the name of Allah, the most beneficent, the most merciful. Professor Pradeep Kumar, Dr. Abhinav Kumar, expert of the today lecture, faculty members, all the participants, and dear students. Perhaps today you are all be motivated to learn a new topic by very prominent professor, Dr. Abhinav Kumar, who is going to discuss on the topic recent trends, challenges and opportunities in AI ML. So be tuned for this session. Dr. Abhinav Kumar has more than 10 years of teaching experiences. Presently he is working as Associate Professor in Department of Electrical Engineering, Indian Institute of Technology, Hyderabad. He has also done his postdoctorate fellowship from University of Waterloo, Canada. He has completed his graduation, post-graduation and PhD from IIT Delhi. Dr. Abhinav is an active researcher developing next generation wireless communication and networking technologies. His research area comprises of EOV communication, wave communications, Internet of Things, visible light-based communications for 5G and beyond. His ongoing work include aspects like energy efficiency, resource allocation, multiple access techniques, security, privacy, and machine learning for communications. Dr. Abhinav enjoys using technologies for his teaching and evaluation in graduate level courses on probability theory, communications and networking at IIT Hyderabad. He is an IEEE senior member and reviewer of very prominent journals like IEEE Transactions of Mobile Computing, IEEE Transactions on Vehicular Technology, IEEE Transactions on Wireless Communication. He has having approx 100 publication on his credit in different conferences, journals and book chapters. He has also done a lot of funded projects like Privacy Preserving Framework for Location-Based Services for Collaboration Kickstarter Program. He has also done DST funded project titled Performance Evaluation of Cellular Network in Unlicensed Spectrum Coexisting with Wi-Fi as a startup grant for young scientists. Also, DST funded projects titled Energy Efficient Lighting with Visible Light-Based Communication and Power Line Communication for initiative to promote habitat energy efficiency. He has also supervised a lot of students for PhD and master's thesis. So this is his brief profile, and I don't want to stand between him and you. So I welcome Dr. Abhinav Kumar for coming here and giving in the control of the session. Thanks for coming here. Big round of applause.
Thank you for the kind introduction. And I'm also associated with the AI department, but just a disclaimer, my core research area is wireless communications. So most of the examples or most of the use cases I'll be presenting will be from wireless domain or at least related to wireless. But that being said, the session is on AI and ML. Again, within AI, I will focus more on machine learning. That's something I use as a technique or technology to enhance communication for next generation systems. So with that as a brief overview, I'd like to start the presentation. A brief outline, maybe initially 10-12 slides will be like a refresher. If most of you are familiar with machine learning it might be a bit redundant also. These are just typical techniques used in machine learning context like supervised learning, unsupervised learning, deep learning, reinforcement learning. And then I'll spend some time on recent trends. What are the typical trends that currently people are following in the context of research or in the industry from the context of machine learning. Again, a lot of it will be ML dominated. So terms like ChatGPT or they might be missing because I do not work in the domain beyond ML in AI. AI is a broader field. I have a next slide just to highlight that part. So I will be focusing only on the learning aspect of it and various recent trends within the context of learning. And then I have 3 use cases where myself and students in my group, master students, PhD students and other researchers that I am collaborating with, we have been actively working in these 3 areas or domains. That includes localization, classification and detection using 5G or similar wireless networks. That would be the first use case. The second use case would be video quality. How can we enhance or how can we perceive better video quality? And the third one would be energy efficiency or green communications for next generation systems. Right? I think based on the time, 11:30 is where probably we are supposed to have a break. I'll try to maybe finish use case 1 or maybe somewhere in the middle of use case 1 we can take a pause. Even use case 1, it's part of multiple studies that have been done in our group. So although we say localization and detection, it can be localization of a drone, it can be localization of a human being, it can be a localization of a car, right? So all those different use cases also, or the studies also have included where we have applied machine learning to do that kind of localization or classification. Right? So to begin with, you might already be familiar with this figure, just to put things in context. So when we say AI is a very broad term. Artificial intelligence is a very broad term. But of course, majority of it is ML, but then there are several important aspects beyond ML also. For example, there is reasoning, there is natural language processing, there is planning. So ChatGPT, in my understanding, comes, let's say, in the NLP part of it, where you are chatting with a client and you have these large language models running in the background, and that is something probably you have another session hopefully on, and I will not even touch in that direction because I am not an expert. Right? I am an end user of ChatGPT as much as you guys are. Right? So I will not even try. What I will focus mostly today's session on is on machine learning, and within machine learning this is a traditional way of looking at it where you have supervised, unsupervised, reinforcement and deep learning. So maybe just to give a brief overview in the context of again communications. Supervised learning, as a lot of you might already be aware, is something where you have data set already there. You have labeled data set available. Using this labeled data set both for training and for testing, you are trying to train some models in a supervised fashion, and then you are using them to label a particular object from test data. And you can have techniques like SVM, naive Bayes classifier, decision tree and random forest, which I presume most of you are already familiar with. Right? But in the context of communications, where are we using it? So there is already a huge amount of literature, huge amount of work that has been done where people are applying these supervised learning techniques, for example, for channel estimation, for localization, which I will also be presenting as part of today's session, and for spectrum sensing. Right? These are some just basic applications. The applications in the context of communication is also very diverse. Right? I'll pick and choose maybe few of those examples as we go forward. The good thing about supervised learning techniques is they work well. Because in some sense, if you look at supervised learning, it's a controlled environment. You have labeled data set for testing and you have labeled data set for training. They're essentially coming from similar domains. So things work out really well. If you are using appropriate technique, you can get maybe 90% plus accuracy without a lot of effort. As long as data is correctly labeled, there are no issues there, it works. The challenge comes again from wireless perspective is the data A is of huge quantity. There is a huge amount of data, right? And the environment also is very diverse. For example, in this room, the Wi-Fi is already deployed, right? I was connecting to one of those to share the slides. That's why I have a bit of delay in starting. Sorry for that. So the Wi-Fi is already deployed, for example, in this room. Right? Now we can use this Wi-Fi network to localize, and I have a couple of slides on this as a use case, where a particular person or a particular device in this room is. This can be done. For that matter, we can use the existing Wi-Fi in the campus, in your campus, to localize in which building, on which floor, within 1 by 1 meter box, up to 99 or 95% plus accuracy, which is a very good accuracy to have, because traditional localization methods do not work indoor. You can try the GPS in your phone. You must be booking Uber cabs and other things. So you must be realizing if you are indoor, accuracy is really poor, especially for satellite-based localization, even when it is assisted by base station. So from that context, it's a good system to have, where if we can apply ML, for example, if we can apply some supervised learning techniques, we can potentially get very good localization. But to do this, you will have to create a labeled data set of 1 by 1 meter of every location in your campus. That is a lot of effort. Somebody has to manually go and take readings, multiple readings at each location. So, because you also need sufficient data. Please note, for example, if I am going to train an SVM, I can't take 10 samples and train an SVM and expect it to work. You need reasonably large amount of data to train these models, and especially in the supervised learning context, the challenge is for every different type of location, in the location example, you need data, labeled data. Collecting that labeled data is very tedious. Imagine your campus itself, it's such a beautiful and big campus, but that also brings the challenge that labeled data set collection for this campus also is a significant amount of effort, right? We also have unsupervised learning techniques, for example, k-mean clustering and all, PC and all, where we do not have labeled data set. We're just trying to cluster things, and we're trying to use machine learning to generate some clusters which can be subsequently used for various scenarios. In this case, for example, in the slide, in communications. Like, now you have multiple base stations deployed, right? Or in Wi-Fi also, let's say you have multiple Wi-Fi access points deployed. When you are trying to connect to Wi-Fi network for your campus, how should the network decide which physical device your phone should connect to, right? That decision in some sense is called user association. So one easy way to solve it is to use some of these unsupervised learning techniques which can be used to cluster. That maybe user sitting closer to the Wi-Fi access point at the back of this seminar hall should connect to the Wi-Fi access point there, and user sitting in the front should probably connect to the Wi-Fi access point deployed in the front of the room, right? And this does not require any labeled data set. So that is the advantage of unsupervised learning technique. But that being said, this cannot be used for all possible applications within the context of wireless, right? It's rather limited to scenarios where we want to cluster users or cluster base stations together without any labels. I will not go into the detail of the algorithm itself in interest of time. The third class of learning techniques is reinforcement learning, where in reinforcement learning, unlike the first two that I have discussed, for supervised learning we train and then we test. For unsupervised learning, we take the data, we feed it to one unsupervised learning technique, we try to cluster, let's say. In reinforcement learning, the understanding is for scenarios where environment is dynamically changing. Something should change. If the environment is dynamically changing, we want to update our model. So for dynamic scenarios, we use reinforcement learning. Again, so here for example in this particular figure, we have an agent. That agent is taking a particular action. Based on this action and its impact on the environment, subsequently the agent gets a return or a reward, right? And also it can change the state of the environment, right? So at every step, user is taking action, it goes into environment, subsequently it is reading what the current updated state of the environment is, and it is also getting a reward out of this environment. And there is a trade-off. Either the user can keep updating the state and become, learn better and better about its environment, or it can extract out the reward, right? That's a typical reinforcement learning model that we are using. So where does this work? One dynamic environment, for example, is again the base station association example that I gave for Wi-Fi. The unsupervised learning or clustering works if you are all sitting, because nothing is changing. So I can take the data, run any unsupervised learning technique, cluster your phones into different access points. But what if we are moving around? For example, there will be supposedly a tea break at 11:30. Maybe we will change seats, so the devices will also change the location. So now runtime, we have to update the association, because now runtime and action has to be taken based on the current environment. We need to update our ML model. Right? I'll quickly grab my model. Yes. So for such dynamic environments, we use reinforcement learning, right? And the advantage is, because of this update, it suits really well for a lot of wireless communication scenarios. For example, spectrum sharing, base station association, or even dynamic parameter optimization. Because in wireless there are many parameters. One simple example, let's say, is handover. If you are moving from one part of your campus to another, I definitely presume it's a big campus. So your mobile phone, which is associated to one particular base station, let's say in this is Hyderabad, right? Or Manikonda. Let's say to a base station in Manikonda, and then you move gradually to your main entrance of the campus. So your phone has to reconnect to a base station, let's say in Gachibowli, right? So this decision has to be done runtime, and for such scenarios, Q learning or reinforcement learning turns out to be a really good model, right? Sorry for the text. I think the alignment has changed. But anyways. Then comes deep learning. Deep learning is typically separately considered than reinforcement, unsupervised or supervised, because in deep learning we are taking these models, let's say neural networks, or these models with transformers or other things in more recent times, and we are training them with huge amount of data. Right? And once trained, then we can use them like traditional supervised learning technique also, or we can also feed them to a reinforcement learning kind of an environment. I do have a slide on recent trends in terms of deep reinforcement learning. So you can use it in the context of supervised learning or in the context of reinforcement learning also. The key difference being the type of the model itself, or the structure of the model itself, or the building blocks that are going into the model itself are slightly different. Right? And again, from wireless communication perspective, we can use them for prediction, from spectrum estimation, from resource allocation, for classification. I will be presenting for object detection and classification as we go forward as part of the first use case. Coming to some of the recent trends, that was the first part of my talk, right? Trends, challenges, and then opportunities. A lot of it will be focused on opportunities, but just to highlight some trends. So in more recent times, domain generalization has become a key topic in machine learning. And I would acknowledge the source, so this is not a figure that I have drawn, you can check out the link. I have shared the slides also. Please feel free to share for academic use. Don't share outside this closed door, because I don't own a lot of copyright. I have just cited the figures. Right. So now, domain generalization essentially means, as you see here, the first three sets, there is a sketch, there is a data set of sketch, there is a data set of cartoon, and there is a data set of art paintings, all of animals. This is our training set data. I want to use this, and now I want to test on actual photos of animals. So original data set on which we are training the machine learning model does not include any actual photos, but the test set data does. This is called domain generalization, where in some sense it is the same class of object. The class of the object is not different. It was animals in the initial set also, it is animals in the test set also. But the distribution has changed a bit. Now this distribution here is represented as actual images or photos versus cartoons and art paintings and all. Right? But the broader class is which animal it is. Those four classes we are trying to determine. Right? And there is a lot of work in recent times that has happened here in this domain generalization. I am going to just briefly highlight some of them, because the whole session can be on this also. But then my objective is to expose you to various possibilities and challenges also going forward. Right? So now, there is multitask learning, there is transfer learning, domain adaptation, meta learning, lifelong learning, zero-shot learning, and domain generalization. I will very briefly try to highlight what are the differences. All of them are relevant, but for specific scenario. Multitask learning means you have multiple types of these classes, S1 to Sn in the training data, and because you are training on multiple classes together, you are able to test on the same classes in the test data set also. And that is why the name multitask learning, right? So the test data is not a different distribution or different data set. It is the same set of data, right, over which you are training, or a subset of it. Transfer learning is, you have a source data and you have some samples from your target data also at the time of training. So you originally trained your based on your source data set, which is let's say SSRC, the source data set. So primarily you have source data set at the time of training, and you slightly update your model to accommodate or perform basis your target data set during training itself. That's one key difference between transfer learning and, let's say, domain generalization. In domain generalization, we are going to test on SN+1. We will not have access to SN+1 during the time of training. Right? That's one key difference. Similarly, we have domain adaptation. But a marginal difference between domain adaptation and transfer learning is, in transfer learning we have the data, the classes are not equal in some sense of your source and target. Whereas in domain adaptation, classes can be same, but the distribution is not equal. So as you see here, the difference is in terms of the distribution. The distribution is slightly different in the context of domain adaptation. And there is also a similarity in some sense between domain adaptation and domain generalization, that your distributions are different. Where you are training and when you are testing, those data have slightly different, or the samples have slightly different distributions, right? So that was a similarity between domain adaptation and generalization, but there is a difference also. And the difference is, in domain adaptation, we do have access to the target training data also. So although we are adapting to a domain, during training itself there is some test or the target data also available. Whereas in domain generalization, we only have access to S1 to Sn, we do not have access to Sn+1 on which we are going to test. So that they are similar in the context of distribution, that there is a variation in distribution, but they are different in terms of availability of data during the training phase, right? Then there is meta learning and lifelong learning. Lifelong learning essentially is you keep learning. Every time a sample arrives, it's similar to Q learning in that perspective, that every time you have a new update, you have new data, you retrain your model. You continuously keep training, and that's why the name lifelong learning. In meta learning, we are trying to extract out what should be the learning model itself, right? Instead of focusing more on, so the classes can be different, but we are trying to extract out for Sn+1 given S1 to Sf, right? The difference is not in distribution, the difference is in the class itself in some sense. The classes are different. Okay. And then zero-shot learning means we have trained up till nth, and then for n+1th, without using it, we are trying to predict, let's say, for zero-shot. Right. But again, the difference is class is different in zero-shot, distribution is different in domain generalization. Right. So there was one recent trend in machine learning where people are using a lot. Okay, maybe I should add to this before we move forward. Where do we use this? So we have discussed so much math and we have discussed so many types of learning models. Where to use which one, right? So one example is, for example, the communication thing that we are discussing. Now let's say there are scenarios where the class is same. We want to detect whether a person is present in a particular location or not. So from an output perspective, output is same, 1 or 0. Which location the person is present, which location the person is not present, right? But what is going to change is, maybe we train for this room and then we predict for a room or another floor in the same building of similar type. So there is similarity, but the distribution is going to be different and the classes are going to be same. So that is where potentially we can apply domain generalization. This way there are, and you can come up with various such scenarios within the wireless context, where for a particular scenario transfer learning looks better, and for another scenario maybe domain generalization looks better. And that's why a lot of exciting work in terms of research is happening in these domains. So you'll keep seeing, if you go back and check, at least from communication perspective, There's a huge amount of work happening now. Let's say within past 5 months, 6 months, you'll see a lot of literature coming up in application of domain generalization in wireless or application of transfer learning in wireless, so on and so forth. For that matter, you can pick any topic that I'm going to discuss today and apply domain generalization on top. For scenarios where the distributions are going to change a bit. One more interesting trend that has happened is a marination of sort. So if you remember my initial slide, there was AI. Within AI, there was machine learning. Within machine learning, there was supervised, unsupervised, reinforcement, and deep learning. But now people are looking at this intersection of deep learning and reinforcement learning. So when we are updating the agent state, can we train a deep learning model there every time there is an update instead of training a traditional model? So reinforcement learning would have some traditional model, maybe a table. So for Q learning, for example, you will have this table. For every action you take or an agent takes, you have a corresponding expected reward. And every time you take those actions, when you are learning, in your learning phase, you can always update your table. You keep updating this table based on the action, right? But now, instead of maintaining that table, and that table comes with a challenge. See, smaller size data, it's fine. You can have 10 actions and you have 100 agents. It's a table of size 10 cross 100. No problem. Right? Very simple table. But imagine wireless communications. Each base station has, let's say, up to 500 users. Each user has an infinite amount of options. I can move in any direction. I can move in any velocity. I can move my phone while moving. There might be different types of obstacles in between. So the variety of options available is too high. So when you map it, and obviously you have to discretize it, but when you map it to a Q learning kind of a setup, the table size just explodes. Right? I'll give an example from resource allocation because I work in that domain. In resource allocation, let's say we want to give for a 4G or a 5G system a particular amount of resource we want to allocate to a particular user. Right? Let's say all of us belong to same operator, hypothetically, any operator, XYZ, whatever, Airtel, Jio, whatever. So now, each of us have a unique mobile phone. Let's say there's a base station in this room. This base station has, in every millisecond, let's say 10 symbols, just to approximate. It's just to make my life easy. Don't quote this number outside the room. It is around this order of magnitude. You have 10 symbols, you have 100 resource blocks, or you have 100 sub-channels, let's say. So total resources is a matrix of size 1000 every millisecond. And now, for every user, runtime, every millisecond, the base station has to decide whether this user should get any one of these resources or not. Right? How many users in this room? Approximately 50. So for every point in that matrix, it can take 1 out of 50 possibilities. It can be user 1, let's say, means number 1, user 2 means number 2, so on and so forth. So 50 is the possibility for one element of that matrix. 1000 elements. So total possibilities are 50 to the power 1000. Now for 50 to the power 1000 sized matrix, running a Q learning algorithm that solves every millisecond, because it has to solve. If it doesn't solve every millisecond, there will be a call drop. Or you are watching a video will stop. I have a set of slides on that also, on perceived quality of video. So essentially, for this scale of problems, traditional Q learning techniques fail to perform because we don't have that kind of compute available. Maybe when we marinate quantum, as the session is ongoing, when we have sufficient quantum resources available for computing, maybe we can use traditional Q learning algorithms on top because we are able to solve for that many states. But the current computing capability we have, even at the base station level, this is not a solvable, this is not a practical approach to apply Q learning directly for a lot of these resource intensive scenarios, right? And that is where this intersection has happened now, where people are talking about deep reinforcement learning. So you take your reinforcement learning architecture, but don't maintain a Q table. Instead of that, you have let's say a CNN. You just update the CNN's weights or update something in your model and keep using this through a deep reinforcement learning kind of a architecture, right? Again, we have done some work. I will not go into the details of the work here because it will digress too much, but just to give you an idea. So this was jointly done with a master's student in our group, Abhinav and Dr. Sai-Dheeraj. This was also partly funded by MediaTek. I should have acknowledged also on the slide, I forgot it. Sorry. So for this particular work, we have used a double deep reinforcement learning framework. Now why this double part? Because anyway, we started with reinforcement learning and now I have hopefully motivated you to say, okay, we should be using deep reinforcement learning because it works better, especially when the state space or action space is too large. And now I am talking about a double deep reinforcement learning. The motivation is sometimes there is overestimation. If you are using just deep reinforcement learning, and typically in deep learning overestimation is a problem, right? That can happen in the context of deep reinforcement learning also. So here we are maintaining two deep Q networks. One online Q network, one target Q network. The target Q network is used to update this online Q network to avoid overestimation. Right? That's one of the advantages. So that is again an area where interesting research is happening on application of, let's say, double deep reinforcement learning for handovers. This is precisely the work that we submitted to ComSnets as a poster. It got accepted beginning of this year. We presented. So again, interesting trend in the context of machine learning. Right? Exactly opposite side of the spectrum. So far we are discussing things which are becoming more and more intensive in computation. There is an opposite end of the spectrum which is tiny ML. So now there is also this work, very interesting work happening in the context of, let's say, IoT. If you have IoT enabled devices and you want to run very basic models on the device itself, how to do that? So for example, TinyML is one such initiative where you do training, distillation, quantization, encoding, compilation, everything on, let's say, a Raspberry Pi board. But then the challenge is you can't use all the traditional methods. But of course you can't run a double deep reinforcement learning setup or framework in a TinyML device. So you have to redesign the whole paradigm. You have to start from scratch from all these perspectives to make sure you are able to run your TinyML algorithms on these really resource constrained devices. The use cases or applications are immense. For example, you must have seen these occupancy detection sensors. I don't see one in this room, but typically you must have seen these PIR sensors, right? Which have these IR light, and if you move, it continues to supply electricity. If you stop moving, it will stop the light. So sometimes it happens you are in a room and the light switches off. At least most of our offices have it. And it's inconvenient because you are in the room, but the device is not smart enough to understand you are still there in the room. And then you have to wave, and then the device works. Right? So we did a study in-house, and is under review, where we were able to show the accuracy of current state-of-the-art typical off-the-shelf PIR devices for occupancy is around 50 to 60%. 50 to 60% occupancy means half the time the device is right, half the device doesn't know whether I am there in the room or not. So you would not like to deploy such a device, and that is the reason, precisely probably the reason that you don't have one such device in this room, because they don't work. 60%, even 2/3 is not a very good accuracy. 2/3 means 1/3 of the time we are there, but the light is going to be switched off. That's very inconvenient. So people are not deploying those devices to save energy because they are not efficient enough. And we did a study very similar to TinyML part, and I am explaining here, where we designed the ML algorithm that was decision tree, and we were able to fine tune it and run it on a Raspberry Pi board. But it could be further optimized, where we were able to get more than 80% accuracy using the same sensor, only changing the algorithm driving the sensor. So we embedded ML into it, similar to the TinyML concept that I am explaining, and we were able to enhance the accuracy from 60% to 80%. And this was some master student work. So much more can be done. There is a huge amount of potential in the domain of TinyML also. If any of you is working in IoT or sensors, then significant amount of research work can be done, which is going to be very different from the kind of works that we have discussed previously. These are all resource intensive works. These requires servers. You need a horsepower kind of server with a lot of capacity to run all of this, right? whereas TinyML is on the other extreme. Between the two, there is another concept which recently is gaining a lot of traction, which is called federated learning. It's like a distributed version, like a balance between the two. The first one, for the matter of all the slides except TinyML, the ML algorithm is typically not running on the edge device. The ML algorithm is running in a server or a cloud, right? But then a lot of times you want, for latency for example, you want to run certain algorithms in your device itself. Let's say our phones. Now phones have reasonable amount of computational complexity. They can run, if a Raspberry Pi board can run an ML algorithm, your phone can definitely run. Your phone has maybe 4 CPUs. Some of them even have GPUs also these days driving, the system. So you have sufficient compute available there, but the compute is not sufficient to train, let's say, a deep learning model on the go. What it can do is it can run a base model which can be updated with inputs from the main server, which is exactly what federated learning is. So we have in some sense distributed the AI model. Each device has its own localized model, but we are updating it by doing, let's say, deep learning at a global level in the server. And with that updated model, we are enhancing the performance on the edge device. Right? So that is where federated learning is getting a lot of traction. Again, in the context of IoT also, but not resource constrained devices in IoT. Because if the device is resource constrained, then maybe only TinyML works. You can't run a federated learning kind of a setup. So those were some of the trends that I wanted to highlight, right, as maybe the first part of my presentation. Coming to some of the challenges that we are facing in the context of ML. First one is the environmental impact. This is one challenge people have started to appreciate, but still not a lot of people appreciate this. How many of you use ChatGPT? Very good. Now ChatGPT is good, right? It works. You ask a question, it gives an answer. Right? A lot of times the answers are legitimate answers. So you feel good, and it's a good model. But what is the amount of power it takes to keep ChatGPT running? Right? That is something probably we have to start thinking also as we go forward. Because these machine learning models, they are not highly power efficient. They are running on GPUs. And those GPUs are being driven by a lot of electricity consumption. Again, please note, you might be using it for research. There are kids who are just querying ChatGPT, which animal has 3 legs, 1 tail, which animal swims and lives on land also. All sort of things people are doing. Now, this in some sense is going to have an impact on our environment. Because if we are going to enable access of such large language models to everybody in the society, let's say from tomorrow, 7 billion people start using ChatGPT. We do not have the computing resource available on this planet for 7 billion people to parallelly use ChatGPT. That is one constraint, computational constraint. Second is, even if we create such computational infrastructure, it will consume huge amount of electricity. So the impact on environment is going to be tremendous. To give you a ballpark estimate, currently ICT accounts for close to 10% of electricity consumption globally. That's a huge number. This was 5% a decade ago. So a decade ago, all consumption, by ICT I mean mobile infrastructure, computational infrastructure, data centers, all of it together, maybe around 2015 kind of a time frame, it was 5% of global energy consumption. And now it is estimated to be close to 10%. And we are nowhere close to everybody using ChatGPT. Imagine what will happen, what is going to be the environmental impact if you are not going to use it judiciously. So although ML is important, it has a lot of applications, it works, has a lot of impact also, we have to be careful. We have to be careful in terms of its environmental impact on how much we can enable given our current energy efficiencies for these models. Second big challenge from machine learning context is explainability. Although a lot of these models work, very recently there is a lot of work which is happening where people are trying to also explain why they work. So to give you a perspective, traditional communications, which is not ML based, it's based out of math. So you take probability theory, you take your linear algebra, you take your or matrix algebra, and we are able to show, or we are able to give certain performance guarantees that with this much probability, let's say with probability 10 to the power minus 3 or less, this system will not fail. The failure rate is going to be less than equal to 10 to the power minus 3. Those kind of performance guarantees can be given for traditional systems because they are designed and you have analyzed them mathematically also. A similar mathematical analysis for these learning models is probably still needed. Some is happening. It's not that nothing has happened in this domain. There's a lot of work. In recent times, if you see typical ML-oriented conferences, you'll see a lot of works on explainability, but I think much more needs to be done. If you're going to deploy a practical system, let's say a self-driving car that senses a human being using a camera, right? And which also brings me to the second part, which is bias. Now, this may sound a bit controversial also, but let's say this ML model, which is camera based, is trained on Caucasian male data set. Caucasian is a white person, let's say. It's trained on a white person, somebody from a Caucasian background. Now, this data set will inherently generate a bias. To detect somebody as human, it can also, and you train a machine learning model on this data set, right? Not the data set, actually the model. When you train a model on this data set where the data is itself biased, then effectively what will happen is, if now all of a sudden I am standing in front of that car, maybe it will detect me as a human, maybe it will not. Because in its data there was nobody which was not up to their typical framework or how they are identifying. Right? Another example being, let's say the data set is completely trained on adults. Everybody in the data set is 5 feet or plus, hypothetically. Now all of a sudden there is a nursery going kid in front of the car. Maybe it will not detect it as a human being. So explainability of your ML model is very important. How it is functioning, why it is functioning, and where it is going to fail. Because see, research and classroom studies are okay. Projects which don't have a real life impact, it is fine. I train a model, it works 99% of the time, no problem. 1% of the time it is failing, it's okay, it's very good. 99% of the time it is working. But we can't do the same, for example, in automotive sector. For a car, if somebody is on zebra crossing and is a human being, 99.9999, maybe 4 or 5 times, it has to detect it correctly. If 1% of the time it is failing, it essentially means 1 out of every 100 person which is going to cross the road is going to get hit. That is something we don't want, right? So there is a huge cost if explainability is not there. There is a huge cost if bias is not removed from machine learning. Bias has to be removed, right? So we have to be very careful what data set has been used to train what kind of real life scenarios, and are there some inherent biases because of the way the data has been structured, right? Third challenge that I foresee is in terms of democratization. For example, now, because you all are using ChatGPT, there is a paid version also of it, right? How much are the charges? Any idea? $20, right? Now, in Indian context, now, maybe $20 is not very high. It is okay. It's not very low also, but maybe it's not very high. It's somewhere okay. Some people can at least afford it. But there are countries where $20 is, let's say, the monthly salary or the monthly expenditure of a household. Now, how do we expect that people from those regions are going to be able to use AI in technology? They can't, because it's too costly for them. So although we are talking about AI for all sort of solutions, for all types of problems, technological problems in the market, it is still on the costlier side. For that matter, even that $20 login that you are talking about for ChatGPT, I think now they have stopped it, they have paused it, because they don't have probably either sufficient compute or they want to restructure the pricing. I don't know, because one of the students was telling me a couple of days ago that they have stopped new logins or new registrations for the paid version. Maybe it was a temporary thing, I don't know, we'll check. So democratization of AI is very crucial. We need to figure out how we can allow everybody across the globe to have access to this technology. This was one example from user access. Let me give you another example. Let's say you want to set up a lab. It is very important to run these models, you need a compute. So if you are going to set up a compute, you need to buy or purchase those servers. Right? Any typical such server with a reasonably good GPU is at least 5 lakh. Ballpark figure. And maybe 3 or 4 students can use it. If there are 50 students and you want all of them to work on deep learning models and all of them to use real world data sets, few gigabytes of information, if not terabytes, then essentially for 50 users you need 10 such servers. You need an investment upfront of 50 lakh. Right? It is a resource intensive area, both in terms of compute and in terms of cost. Right? So we need to think more how to overcome these challenges. There are approaches where maybe you can borrow some compute online on these cloud computing platforms, but they are also not very cheap. Anybody doing that? Anybody using AWS or similar service? What kind of monetary thing we are looking at? Ballpark? Like 100 rupees a month, 1000 rupees a month, what is the ballpark for such an access?
129 per month for single data service.
How many cores? It's a core based service like these many cores, or it's a compute based service? Compute based. So I'll give you an example. I can openly give an example from my own institute. So we have a portal which gives you 70 paisa per minute per core. And this is open to you guys also, by the way. So if anybody needs access to compute, just check out I think Swayam portal at IIT-H or drop me an email, I'll connect you. So there is this cloud computing facility or supercomputing facility available where you can rent cores. So you can rent a CPU core for 70 paisa per minute. But 70 paisa per minute, although sounds too small, but let's do the math. Let's quickly do the math. 70 paisa per minute means for a day how much do you have to spend? Ballpark. Any idea? You can use your phones, don't worry, this is not a quiz. I just need some help. I don't want to take my phone out and do the
24 hours into 60 minutes
Yes.
into 60
0.7.
seconds. 1 minute is for 70 paise.
Yes.
1 minute.
24 into 42.
Yes.
4, 8, 2, 4, 10. 1008.
1000 rupees. Ballpark.
Into 207.
That is for 1 day. So for 1 day you are paying 1000 rupees.
Nahin, it's 10.
Or 100 rupees.
1080.
Nahin, it's a 1,80,800 rupees. Because 24 into 60 into 70. 24 into 42 is 1008. So 1800. So 1,800,000.
For 1 day?
ma'am.
No, please check. I think ballpark 1000.
1080
If
rupees.
it was in paisa.
Acha, 70 paisa.
Paisa.
Okay.
Yes.
1080 rupees.
1000 rupees.
1,080 rupees.
So even on a government portal, if you are renting a core, you have to pay 1000 rupees a day. Now you rent 5, you have to pay 5000 rupees. GPU costing is 4 rupees per minute. This is CPU cost I'm telling. GPU is ballpark 4 rupees. Right? So again, 5 times roughly. 5000 a day you have to pay for 1 GPU access. So even though there are rent, and this is supposed to be cheaper than Amazon probably, I don't know. Whether it is actually cheaper or not, I don't know. I also am not sure what kind of compute resource we are offering and they are offering. Maybe that's a study in itself. But what I am trying to highlight is, even though there are options available where distributed computing facilities are there, they are still not cheap enough. If you are running a resource intensive model, their resource intensive can be intensive in terms of computational requirement, more cores, more GPUs, or intensive in terms of memory. Because if you go online for these third-party cloud-based facilities, they have a matrix, either this much memory or these many cores. If you exceed any of that, more money you have to pay. So that is a challenge and that has to be resolved. That's a key challenge that has to be resolved as we go forward. Right? I have already talked about bias removal. I'll quickly move on to privacy and security. For example, for all of you who are using ChatGPT, whatever you submit there is accessible to others. Right? Anything you share, so and it is in your terms and conditions itself. You can't sue ChatGPT after you have chatted with it. Because when you subscribe, you agreed to saying whatever conversation you are having is available for other users also, will be used for training for other users, and other users can potentially access that data also. So what happens to privacy? Because see, this is a very different kind of audience. Right? This is in a technological institute at grad, postgrad, PhD, faculty level. So the level of awareness here is very different. But imagine first year BTech students. They may not know, they may not even read those terms and conditions. So what happens to user privacy? Right? What happens to security? If we are, and this happened for that matter, there was an incident, I will not go into too much detail of that. Somebody was trying to share some research information, defense related, and chatting with ChatGPT. And this is from a country which is directly in conflict with the source country of ChatGPT. So effectively, unknowingly, some state secrets are revealed. Right? So both privacy and security are challenges that have to be resolved in the context of machine learning. A lot of awareness has to be created. Right? Lastly, quantum. I see it as a challenge because of two reasons. Unlike, although the whole session itself is about quantum and ML, but there are two key challenges I foresee from quantum perspective. One is, even now with limited computational capabilities, some of the machine learning models are performing exceptionally well, like LLMs in the ChatGPT context, or reinforcement learning or deep learning models in computer vision problems, image processing, image detection, image labeling and all. They are working like 98%, 99%, that is the state of the art in terms of accuracy. And this is happening with limited compute. When I say limited, I don't mean 4 cores, 10 cores. Limited, I mean in the context of quantum. Compared to quantum computing, the compute that we have is still rather limited for each of these use cases. But what will happen once we have quantum computing and we are able to marinate it with ML? The kind of scenarios we can foresee is really challenging. Imagine GPT. GPT is running on traditional computing architecture. Now imagine replacing that traditional computing architecture with qubit-based quantum computing facility. The kind of intelligence level that machine learning model can have will easily surpass collective intelligence probably in this room, or maybe for a larger audience, which is scary because essentially we are going to have a machine which is much, much smarter than a human being, or the collective human consciousness. Because that's a very scary scenario, right? Because this machine can and although it may sound filmy and all, you must have seen Terminator and whatnot, so you are aware of hypothetically what are scenarios are possible. Those scenarios don't look hypothetical once you marinate quantum with ML. Because with quantum, you will have, or we will have, that sufficient computational capability available. Right? That's one challenge. Second challenge that I foresee is the way quantum has evolved and the qubit-based architecture has evolved both in quantum communications as well as in quantum computing is not currently completely similar to the way ML has evolved. ML is based on, let's say, the neural networks and representation of information in a discrete set of architecture. How do you apply the two? How do you marinate the two? That appears to be a very interesting research challenge to me. How do you combine the two? It is non-obvious. I believe there were some other experts who had a lecture, but even I am open to attending some sessions on this, on how to apply machine learning on quantum computing based architecture. I think this is a very exciting topic, and that's why a very timely sessions, workshop you guys are organizing here, because it is non-trivial. At least to me, it is non-trivial. So I also look forward to maybe more on this on how to marinate the two, how to operate. Because it's not that quantum communication is not happening. It's already happening. There was a demonstration, I think, by China, where they were able to send, I think, 16 qubits over a few thousand kilometers. So that stuff is taking shape in real life. It's not that in 10 years we'll see some quantum communication happening, or in 10 years we'll have some quantum computing device. Very soon we are going to have deployment of them. And then once you combine that with ML, it is a very dangerous or risky scenario, at least the way I see it. Right? So those are some of the challenges I wanted to highlight. I will not spend a lot of time on them. I will move on to the other part of my session today, which is on various use cases. So first part was typical ML algorithms and how recent trends have evolved in the context of machine learning algorithms like deep learning, double deep reinforcement learning, tiny ML, federated learning, so on and so forth. And then I have highlighted some challenges. Again, this is not an exhaustive list. There are many more. There are several challenges from humanities side, but then probably I am not an expert. Maybe a break now? Okay, great. I think then good time. So maybe let's take a break here. I have 3 use cases based on the time that is available to us. I'll try to complete as many of them as possible. Thank you. We'll pause here. I'll start with the use case subsequently after tea.